Okay, so this is explaining subsurface tracts, subsurface reflection points, and this is something that over the years it appears to be confusing to a lot of people. At one point it was very confusing to me, and so I'm doing a video on it that hopefully helps somebody. So I had already done this illustration. I was doing a video earlier, I didn't work out, so I'm doing it again, and this is explaining. I'm just going to use one shooting episode, or what will I call it, to one reflection on the same cable from two guns. Now, if you have to know the number of subsurface tracts or position you have, the simple calculation is the number of gun times the number of your shooting lines or cables or your shooting short lines. So if you have two guns you are using and you have 4 cables, then you have 8 subsurface tracts or 8 subsurface positions. And if you have, as in this illustration, you have 8 cables and you are using 2 guns, usually they are shot in flip-flop position. Flip-flop position simply means you shoot this, you move a certain distance, and then you shoot the other one. In flip-flop position, it is going to it's the usual, flip-flop is the usual method that is used. So if you have 2 guns you are shooting, you are going to, whether you use flip-flop or not, but if flip-flop is better for configuration of gathers, you are going to have 8 times 2, 16 subsurface tracts. Now, in simple short explanation, when you shoot for this gun, though sincerely we are supposed to put let me insert one shape. So we are going to, in practical, let's say you are shooting every 50 meters. By the time you are shooting this after you shoot this, if you shoot this first, the next shot should be at this position, because the vessel would have moved a certain distance. Usually it's half of the spacing distance, so let's say 25 meters here. Okay, so after you shoot this first gun, this position of this gun will be here when this one is shot. So now let's try and replicate this and do it, explain how it's going to be in reality, so that I will not spend a lot of time here. I'll just copy these two and place it in a new window. Okay, so let's bring our new shot position into this as well. So taking I want to do a V shape, so let me use this, and this is not what I want. Ctrl Z. If I can't get that, I will just, okay, let me use this. This is good. So using this, let's say we are talking about this receiver. Using Snare's law, the receiver position will be at the midpoint between the shot and the receiver. So because I want to include the other shots, let me still move this forward. So this is representing the subsurface, because this is a marine acquisition that we are illustrating here. So this is the water bottom. This is illustrating the water bottom surface, and this is, let's say this is where, this is the point where it meets the water bottom. Now because we are, the water bottom from the shot will be the same distance, assuming that there is no undulation in this area we are looking at. It goes therefore to say that this reflection point should be similar, there is the time, and the time travel to the water surface should be the same with this new shot position. Okay, I hope you understand that. Fill. Okay, so which means that when you shoot from this position, and the wavefront, as already explained here, you shoot, the wavefront travels in different direction. We are looking at a particular wavefront. It comes from the shot, and then is reflected and recorded by the receiver. So this is just a simple line rule that we use in school. Why the actual what is actually happening in reality it is more like this. So using that, establishing that this was shot from the same distance above the sea surface, the water bottom, then it means that at this point it will take about the same travel time to reach the same water bottom. So let us duplicate this, Ctrl D, please. I hope you understand. Okay, let us distance from the shot to the, we are assuming that there is no undulation on the subsurface, the water bottom. So therefore the distance from this shot to the subsurface should be the same with the distance from this shot to the subsurface, because you understand that this is like it's a 3D should I format it to picture effect 3D rotation? Yes, it's like more like this that we are actually looking at. Let us use it to explain subsurface track. I hope I'm comprehensive. So it will mean from here to here. Now on this receiver, this cable, let us take it to this cable. To be received by this cable from this gun to this same first channel, you see that the place they are on the subsurface is not the same because of the gun position that is different. The first one, we measure the line of the first one so excuse me. So we measure the line of the first one and we'll call it a track 1, or usually you name it from where you want. For example, we name track 1, 2, 3, 4, 5, 6, 7, 8, and then we'll come back to 9, 10. You can decide to change it to track 1, the next one track 2, track 3, track 4, track 5. It depends on the processing company, however they want to do it. So but usually most people just use track 1, 2, 3, 4, 5, 6, 7, 8, then come back 9, 10, 11, 12. You can use a mathematical computation to name them. Very easy. So this other one is now on a different line. If you repeat this process for all these other receivers, the first gun, the distance to, let me just do that. First shot to this receiver, then this second shot, Ctrl D, to the second receiver. You see, these ones are this gun along the same cable. They are forming on one particular subsurface tract. The other one, they are forming on the same floor. If you continue, you will see these reflections on from one gun to the same cable or streamer. They will reflect off a particular subsurface tract, while the other gun on a particular cable streamer will reflect off the same subsurface tract. So I hope that is a simple and clear enough on how subsurface tracts are formed and are measured in seismic data processing. Thank you.